While we're talking about carbonyl-containing compounds, the other thing we should address is the presence of conjugation. Now, conjugation usually occurs when you have a double bond, single bond, double bond pattern here. So two pi bonds separated by a single bond. That's conjugation. So, and there's some delocalization of electrons in there, and it turns out that's going to actually lower our stretching frequencies for carbonyl, for carbon-oxygen double bonds. So in this case, we're going to look at some minor resonance contributors to kind of explain it. But we can kind of see here that, for 2-butanone here, so that signal showing up at 1718. So, but conjugated with an alkene all the way down to 1695. So in this case, conjugated with a benzene ring. Notice double, single, double. So pi, single, pi. So down to 1691. And then over here, we can actually see that there's be some conjugation with the lone pair on the nitrogen. So, and that's why the amides actually shift so low. And in this case, I forgot to put it on there, but this is around 1674. I've kind of got the average amide at 1685, but they're commonly lower than that as well. But this one's at 1674. And if we take a look at what's going on here, we'll look at some minor resonance contributors for all these molecules. So with this polar carbon-oxygen double bond, we can kick the electrons up to the oxygen and show this minor resonance contributor. So now the oxygen's got 3 lone pairs, negative charge, it leaves the carbon with a positive charge. So, and in this case, because there's charge separation, this is not as stable as the original resonance structure, and so this by far is the major resonance contributor. And, maybe we say that this is 98% major resonance contributor versus 2%, and I'm making these numbers up just for the sake of argument. I think with the numbers will add something to our discussion here. So if we look at the next one here, so we can, you know what, let's get those arrows out of there just for the fun of it. So make some room there. So going back here, if we do resonance again, we can kick the electrons up to the oxygen. So, but in this case, the carbocation's 1 bond away from these pi electrons, and we'll get 1 additional resonance structure. So, and that's going to explain the difference in the stretching frequency here. So again, let's just say that these correspond also to a 2% contribution here. So because the additional resonance structure, maybe the original major resonance contributor with no charge separation now only contributes 96%. So, and as a result here, you're going to find that with only 96%, look at the carbon-oxygen double bond. Double bond in this structure, single bond in the other 2 structures. And so maybe in this structure we say that that double bond in the real resonance hybrid, in the real structure, is 96% double, 4% single. So, but in the example above, here it's a double bond, and again, here it's a single bond. And so up in this first one, we might say it's 98% double, 2% single. And so as a result, it's actually closer to a double bond and a stronger bond for the top one, and a weaker bond, a little bit less double bond character, for the one below, the second one here. And so a stronger bond is going to have a higher stretching frequency, explaining why this one shows up at 1718 and this one only up at 1695. So if you just memorize that resonance always lowers stretching frequencies, that's not technically true. For a carbonyl bond, it generally is true, but don't just memorize that as a general rule. It's not generally the way it works. But for the carbonyl, it is how it works. But for other bonds, maybe, maybe not. So I can envision your professor wanting to make sure you really understand this concept and asking you about conjugation for some other bond besides the carbonyl. Be careful. So if it increases the strength of the bond based on greater double bond character, so versus does it decrease the strength of the bond based on like less double bond character, as is the case here, that's kind of what you'd be looking for. But again, for a carbonyl, so conjugation is going to lower that stretching frequency. So we'd see the same thing for in this case, acetophenone. So I could show a bunch of resonance contributors there as well. So, but I really want to look at this amide for a second. So for our amide, we could again do the same kind of thing. So let's get black going here. So single bond up to the oxygen, carbocation. So, but the lone pair on the nitrogen allows us to kick a couple electrons in there and get 1 additional resonance structure like we did above. That leaves the positive formal charge on the nitrogen. And so again, we see that in one of the resonance structures, and definitely the major resonance contributor, we've got a double bond here, but in the other 2, a single bond. So, but we've got a little bit better resonance contributor off to this one on the right here than the one in the middle. And so maybe it's like, 2%, but maybe this one's 4%. So, because every atom here's got a filled octet, including the nitrogen, who's got the positive charge. That's one way to look at it, or you just have more electrons in bonds. Either way, this is a better resonance contributor than the one on the left. That might leave this first one only having 94% double bond character, overall a little bit weaker than even the ones we've looked at above, and therefore an even lower stretching frequency. Now, if we compare this to an ester for a second, so we could look at the same thing with an ester. So, and it turns out that oxygen is just a little more electronegative than nitrogen, or actually it's quite a bit more electronegative than nitrogen, and as a result, you get that third resonance structure with an ester just like you did for the amide here, but the electronegative oxygen actually destabilizes the resonance structures that we can draw as well. And as a result, overall, it actually ends up shifting to a higher frequency. It actually has weaker resonance contributors than all these others that we've drawn, and ends up actually shifting to higher, and that's why your ester, carbon-oxygen double bond, having less stable resonance contributors overall, shifts at a higher frequency, not lower, at 1735 wave numbers here.